When's our test of data for Thanksgiving? It's the same day as our Robin session.
Today's slides are really lame, so I'm not going to be talking from slides too much today anyway, but I did want to show you the pictures of our program for the hour.
Post it again, it's on the same day.
And our boiler.
We're talking about Wheeler?
Boiler.
It's a real one.
No.
He's my favorite.
Not the oil one? Not the one that has a lot of oil?
Or kind of just use like another one. Which is like the two variables, two random variables. 5, 6, 6. So it's like the same thing, it's just another function variable. It's like Calc 3. Calc 3 just do it.
Right.
Yeah.
I just hate it when there's two computers. I'm trying to use the mouse from this one.
Integration. I forgot how to integrate.
That's very relevant to your education.
It's yeah.
It's the foundation for my education. I don't know the basics. I don't know I can sure.
So as you can tell, I did these slides at 2 a.m. It's not November 8th, is it?
I missed the test.
Okay.
It's an even number.
You're good.
Yeah. So up to equivalence. So what have we done thus far in my giant list of mathematicians we can't miss? I have to say the Bernoullis, you know, I don't think I did them justice. Like, for instance, we haven't even talked about Bernoulli numbers. There's a whole category of numbers named after Daniel. I can't leave the Bernoullis without saying this one thing about Daniel Bernoulli, because I discovered this when I was an undergrad, and it just freaked me out. Because remember when you do Riemann sums? Not everybody's done Riemann sums, but one of the things, there's a set of formulas you have to sort of memorize to deal with Riemann sums or polynomials. Like, let's actually write some formulas down. If you write the sum of just the numbers, I, where I starts at 1 and goes to some number, that's n times n plus 1 over 2. If you replace the I in there with its square, does anybody remember the formula for that?
No.
Like n squared.
It's n times 2n plus 1.
Times n.
No, but there's another bit in there. It's n times n plus 1 times 2n plus 1.
Right.
All over 6. That was the hard one. And if you were doing Riemann sums in calculus, where would you use this if you were trying to do a Riemann sum involving the function x squared? But anyway, that's the hard one. The last one people usually memorize is the sum of the cubes, which goes from 1 to n. Because the answer for this is just the square of this one, so it's actually pretty easy to remember. It's n times n plus 1 over 2, the whole thing squared. Or if you like, you can write it as n squared times n plus 1 squared over 4. But has anybody ever done the sum of the fourth powers?
I'm gonna guess it's the square of I squared.
That'd be nice, but no.
It's the cube of I squared.
No. It does involve n's and n plus 1s and 2n plus 1s and other things, but
I'm gonna guess 3n plus 1.
we can't keep just guessing. I guess you could keep guessing. Maybe eventually you'd get it.
We'll class it out eventually.
Yeah, it would be just killing our time here. So there's a pattern to it, and this guy, Daniel Bernoulli, kept going with this table until he got down to the sum of 10th powers. That's right, I to the 10. And he has this horrendous formula for it, but you know, it's a formula. And inside this formula, you'll find numbers called Bernoulli numbers, because of him. And then here's the quote from Daniel Bernoulli. With the aid of this table, I was able to find the sum of the first 1,010th powers is equal to, right, he wrote out this giant number, in about a quarter of an hour. Okay, why? Why did he do that? But still, I mean, you know, it's just an incredible accomplishment. Most of us are happy with just memorizing these first three. And actually, the 1 or 2% of the population that gets that far in math is happy with just this memorization. He took it farther. He went all the way to the 10th powers. He stopped there, but he could have gone even higher with the powers because he developed a general framework for it, and involving Bernoulli numbers, and was able to take the formula and then apply it with n equals 1,000. No computers, no calculators. Not even, I mean, I don't think he could have done an abacus work on this. It was just,
So what's the general formula for I to the K?
that's a very nice question, and it involves Bernoulli numbers, and I'm not going to talk about it. Plus, you know, do you think I actually know it off the top of my head?
Of course you do, you're very smart.
I've got Google, I could go Google it.
So
But what really, when I was an undergrad, what was cool about this moment is I actually went to the library and looked this up in a book, and it was his original text. You know, so he was one of the ones who wrote something in English, and I was able to look at, you know, his original article about this thing and read his original words. That was a moment that I still cherish. It was kind of a cool discovery thing. Anyway, I've lost my screen. I don't think it's a screensaver, I think it's the battery saver. I thought the battery had just died. Let's just plug it in to make sure that doesn't happen. So with that, talking about Bernoulli numbers, I think I'm gonna say we're kind of done with the Bernoullis. So Euler is our next guy. Now, I just want to say the pronunciation. A lot of people are still saying Euler. I hear it. Math majors saying Euler is not. Got to get on board with it. He's Swiss. Like the Bernoullis, his family was originally Belgians, and they fled the exodus from Belgium when the Spanish took over. So he's in Switzerland also as an expatriate. You may remember his name came up when we were talking about the Bernoullis. I believe it was. Which is the one who went to St. Petersburg? Yeah, he went to the Cone place. He went to the Cone place too. When the Bernoulli brother left the Cone place, he became the big dude at the Cone place. And like how we're calling St. Petersburg the Cone place.
That's what I came up with. No place where people die.
Lots of people died. Ask the Nazis. They had a very terrible time. Except it was called Leningrad, I guess, when I think there's a movie about that.
Like Stalingrad?
Was Stalingrad or Leningrad? Stalingrad.
Yeah, I saw that. It's a real upper that one.
Okay, so there he is. That's as an older man, I guess. This headgear he's wearing is a typical Flemish thing. So
What is that hat he's got?
yeah, it looks like he's got a rag on his head. Really, it does. But that's a sort of a bonnet. Yeah.
So, does he just have a menstruating hairline? Is he bald? Like, or he's just got a big forehead?
He
Looks like
definitely-
he's got no hair under that hat.
So it wouldn't be atypical for men at that time to shave their head, even if they weren't bald, because of lice.
Okay.
So a lot of people shaved their heads and wore wigs, because you could fumigate your wig, you couldn't necessarily fumigate your hair. But I don't know whether he was naturally bald or not. To be honest, I'm not sure if anybody but.
So would he be considered stylish back in those days? Is it?
This is him sitting for a painting, right? This isn't like something from a Snapchat thing. This is him sitting for hours while somebody painted.
I gotta say, he looks better than a lot of the guys we've already talked about.
Yeah, I'm thinking this is his good outfit that he's wearing for the.
So he just had to sit there.
It looks like pajamas, doesn't it? And what's this weird thing on his head?
Instead of wearing his best nose, what's wrong with that?
His nose is entirely natural. I'm glad you raised the issue. Does anything strike you odd about his eyes?
Yeah, he has a lazy eye.
He was completely blind in that eye.
Oh.
So he blames the blindness on stress, overwork of the eye, but other people have said maybe he had a cataract now. They're looking back at the way he described it. It doesn't make sense that he just lose vision from overstressing and reading too much by candlelight.
Surely you have one eye.
Well, he lost sight in the other eye too.
How did he do word blind?
His memory was that good. And he had good helpers. So two of his sons helped him out at different times, and he had another gentleman whose name is escaping me who helped him. So he had people to do the actual writing, and then they would read stuff back to him, and he'd go, no, that's not right. You can imagine the process with a blind super genius.
Better,
helping
had
him
the
out.
magical midget, right?
Tycho Brahe with his widget.
Yeah, that's probably better.
Well, this guy was an incredible mind. He's probably the most
No, I'm not
productive
saying he was
mathematician of all
smarter, I'm
time.
saying he had the better.
I know, but his son was one of those helpers. Now, he had two sons. One was a mathematician, and the other became an army officer. So
The guy with the
like him?
elk and the midget, those guys are.
it's
they're up
really
there.
hard to beat Tycho for the little oddities that he had. He had some pretty good stuff. The version I heard about this blindness was that it was from cataracts, and that this is 1700s, right? He took a very early experimental surgery to remove a cataract.
Oh boy.
And then that's why he lost the vision. But
Oh.
what I just read last night didn't corroborate that, so now I don't know. They did say that when he began to lose vision in his remaining eye, it was because of a cataract, and they tried to do a surgery. Now you're blind in one eye, and they do a surgery on your one good eye. You would take care of this, wouldn't you? Euler seems to have forgotten to do his post-operative care, like washing the affected eye or whatever. So he had his sight back for like 6 days, and then totally blind in both eyes.
He's one of those ones who gets so lost in his work, he forgets to do everything else.
I think he might have had a little absent-minded professor. Yeah.
Well, see, then his son should have been on top of that and been washing his eyes.
Dad, did you wash your eye? Yeah. Maybe the son had some of this going on too.
Absent-minded professor, how can you absent?
It's easy to envision them both as being on the spectrum. I mean, really, you know what I mean? Oh crap, I went past it. Let me go backwards. Yeah, there we are. So this is our man Euler, and even that picture of him on the money from Switzerland.
What is that?
Bank Nationale Suisse. You can see that these guys were multilingual in Switzerland. Here it is in French. What language is that? Bank
Italian?
Nationale?
That's
What is
Italian.
that? Yeah, that's Italian. Where's the German?
Swisher.
Yeah, that's it. Spicer National Bank.
What's the thing on the bottom? It looks like a toilet.
So what do we got going on there? Jeez, they're trying to, in one picture, show a bunch of the stuff that this guy worked on. But it's not possible to do in one picture. There's something about acoustics there. There's something about chemistry. You see the orbital things there? That looks like chemistry.
Yes.
It can't be, because I don't think they had an atomic model of the atom yet.
What's
It's
wrong?
Is that a propeller?
a propeller.
Or
One of the things on here is orbits. The big green things are elliptical orbits around the sun, and that's a comet's or an asteroid's orbit, a highly elliptical orbit. I don't know. There is definitely something about sound in here. That thing is showing nodes on an acoustic array. And it's Dix Franks, D-I-X Franks. You know what that is?
$10.
Dies is 10. Yeah. This is the 10 franc note.
It shows on the
Zero on
other
it.
side as well.
Oh yeah, there's a big 10. Okay.
Almost
Yeah,
said we were a decimal. The words, made it very clear what it was.
good point. So I don't know. I think that's pretty awesome to have a mathematician on your money. We have people who really were not cool on our money. Some of them, like, we're ready to replace Hamilton, I think. I don't know.
Jackson.
He's on the 20?
Jackson.
Oh, it's Jackson. It's on the 10. Yeah.
No, Jackson's on the 20.
If I got it backwards, I don't know if I have
Hamilton is on the
it.
time.
But anyway, one guy is like a Civil
Hamilton's
War
on-
on the wrong side hero, so we don't want him. I don't have any.
Jackson's on the 20.
It turns out George Washington is on all the singles that I have. So that's Euler. I gotta talk about some of the things he did, but literally, it's an impossible list. I was trying to pick and choose what are the fun things to talk about.
Like the entire class, like for the entire semester, would just be a boiler, right?
It would, there is a book about Leonard Euler written by a historian that I'm very fond of, William Dunham, called The Master of Us All, and it's 200 pages. And it would make an excellent textbook for a course that was just about Euler. And it wouldn't be like a dull course, because he did so many different things. He had his fingers in so many different pies. You would have a good time with that course. But I want to pick on a few of the things he did, and this goes, first thing I'm going to talk about goes back to one of the people he met when he was in St. Petersburg, and so the Catherine the Great, she was the descendant of Peter, what's his name, Peter the Great? I think they're all great. So she wanted to establish a really impressive university system, and so they got it started in mathematics at least with one of the Bernoullis and Euler and another man named Christian Goldbach. Goldbach is have you heard of Goldbach's conjecture?
I've heard of him, I don't remember what it is.
So Goldbach's conjecture was horrible. It was this really complicated thing about how you could always do stuff with prime numbers and always get something. But Goldbach's conjecture, filtered through Euler, came out as this. Every even number is the sum of two primes. Every even number greater than 2, because 2 is not going to work, but because 1 isn't part, right? But 4 is 2 plus 2. 6 is 3 plus 3, 8.
5 plus 3,
5 and 3 does it? 10?
7 and 3.
Or 5 and 5. That one you can do it more than once. That's interesting. 12.
7 and 5.
7 and 5 works. Can we do it another way? 3 and 9 would be good. I guess we're okay. So, but you see how that pattern works? You can. It's still unknown today whether this is true or not, but almost everybody believes it. I'll show you. Switch to GC.
I'm going to prove it. Call it the Jefferson axiom. Wait, no, that's not the right name. Here.
I like this particular image because I personally uploaded that to the Wikipedia. Cool. That's an image of how many ways can you write 2n as a sum of primes. You'll see that, down here it's a small number of ways, but when you get up to larger even numbers, there's lots and lots of ways to do it. And you see there's colors on there that seem to illustrate something. There's more greens and blues down here and more reds up there. That's what the even number is on a 3-hour clock. So what is it if you reduce it by 3? So what is it? The things that are multiples of 3, can be written as sums of primes more ways than things that are either 1 or 2 by 3. It's weird. There's interesting connections in there, but nobody quite knows the answer. So that's still unsolved. But the point was that Goldbach made the conjecture, and he made this really weird, complicated thing. And Euler said, no, that's equivalent to this.
It would never really be solved unless they contradicted, because everybody.
Well,
Get
there
through
has been
everything.
there has been progress. There has been recent progress, and not in the form of we've checked now out to 20 billion instead of only 10 billion, because they did that for a while. But recently, a man, kind of a teacher at a school is a bit like Southern, University of New Hampshire. He was one of these guys that just nobody thought anything great was ever going to come out of him, because he did his thesis work 20 years ago and then he just worked as a calculus teacher forever. And all of a sudden he went, here you go. And he produced this paper that proved a thing called the bounded gaps conjecture, which is the first real progress toward improving this that we've seen in about 100 years. So this may get cracked soon. The man's name was Zhang. I forget his first name. Charlie Zhang. So he's a local hero nowadays.
Did you give us an idea of what he said?
Bounded gaps says that that there is some number so that the gap between primes, eventually that gap happens infinitely often. And the problem is we don't know what the number is. But Charlie's proof was that that number is smaller than around 6 million. And somebody recently has taken his line of reasoning and sharpened it up, and now it's less than a couple of thousand. So the gap between primes of a couple of thousand occurs infinitely often. That's not necessarily the case, right? You could get to the point where the gaps between primes just get bigger and bigger and bigger, and we never see a gap of 6 again. But we will.
Are two primes relatively prime to themselves?
Yes, being prime implies relative primality. If either one of the primes is prime, and the other one doesn't involve that prime. The two distinct primes are relative prime. If they're the same prime, then no. But I don't think you meant that. So that's one question that came to whether via Goldbach.
I'm trying to solve it.
I'm pretty sure the Königsberg Bridge problem also came to whether via Christian Goldbach. But I might be wrong about that. But so let me tell you a little bit about Königsberg. This is a city in what's now Russia, but let's see if I can find you a map, because this is an interesting bit of geography.
Kaliningrad Oblast.
Kaliningrad Oblast
Oblast.
is a what is it called?
It's
Let's see if we can spot it on a better map. Now that one's pretty good scale. So the light green is Russia, and so is the dark green. There's this little chunk of Russia that is up here on the Baltic Sea. Other countries near there are Lithuania and Latvia. There's another, I forgot the names, Lithuania, Latvia, and
Estonia.
Sorry?
The Russians actually have a military outpost in that oblast.
They also have a shipping facility there. It's a big port. But Kaliningrad now was Königsberg back in the day. And Königsberg spelled. They also, by the way, there not only is this thing, they don't show it on the map here, but there's a train line and a highway that gets to there. So they just sort of said, look, Latvia, we need this, and you're giving it to us. And that's the way that worked. Anyway, why would Russia want that little thing there?
They needed a warm water port.
Yeah, that's not a warm water port, but at least the Baltic Sea can be cleared with icebreakers. Right, so the rest of their ports up on the north part there, that's in the wintertime, they're totally useless. And they also, well, they have some access to the ocean through the Dardanelles. This thing here can get you down into the Mediterranean, which is probably why they recently did some. There was a little military thing in where the Russians took over
Crimea.
that thing.
Sebastopol region.
So yeah. Anyway, about Kaliningrad. I mean Königsberg now. Königsberg means the king's town, and this at the time was in Prussia, which doesn't even exist anymore. But think of it as sort of halfway between Germany and Russia. Prussians were really famous in the American War of Independence, by the way. They were the mercenaries that the English sent at us. Big, tough guys who grew up in a horrible climate, and they were hard soldiers. Anyway, Königsberg looked kind of like this. It's on a river, the Pregel River, and there's roughly 4 parts that are going on. There's this island. There's the the north branch of the river and the south branch of the river. There's a promontory up here. We had the island, a promontory, the north bank and the south bank of the river. And there was a collection of bridges that went around these things. And apparently this is another mathematical tourism thing. These bridges are still there with one exception. But there's more bridges because this is like highways got built. These old Roman style bridges were built. One between the island and the promontory, two each between the island and the shores, and then also some crossings of the river up here and up there. So it's a relatively small little medieval city, and people would often take promenades on Sunday afternoon. You know, after church, you're still wearing your nice clothes, take a walk around town, just show yourself off a little bit, meet your friends and neighbors. And somehow somebody came up with this question. We've got 7 bridges in town. Can we take a little walk, a little tour, and cross every bridge once?
And only once.
And only once, right? Once. So in a way, you don't have to say and only once. Just cross it once. No more. No?
You already went over this with me.
Yeah, we know the answer is no, right? So what happened with Euler, he was handed this picture, and he converted it into a graph. So Euler invented graph theory from this problem.
Yes, first reference.
I should have got capital graph theory. Or this. So yeah, we have dots where the various land features are, and we have connections between those dots. The 2 bridges connecting the island to each of the banks, and then 1 bridge between the island and the promontory, and then 4 bridges here and here. And the question turns out to be a very simple one about the degree, that is, how many edges leave a particular node. There's 3 coming out of that one, for instance. So ask yourself if that place could be where you start or where you end as you're taking this tour of the bridges. Suppose you start here, then you've got to leave, you got to come back, and now you got to leave again. That's doable. So that could be a start point. But all 4 of these are odd. Does that mean we can start at any of them?
One of them's
We got 5 here,
No,
3,
fine.
and 3, and 3.
I can count.
The problem is, if you think about, could that guy be in the middle of our path? Well, that means we would come in, and then we would leave. Uh-oh. We'd have to come in again and get stuck. So a thing that's odd can't be in the midst of the walk like this that covers all the bridges. And everybody's odd. You're hosed on this. This makes a great quiz question. I want to give you guys a quiz on this.
This one's not too bad. I think
Yeah, but I can see, now that we've generalized it, I don't have to stick with this medieval city. I can just draw a graph. Right? I can say, okay, here's a collection of 5 dots. And I'm going to put some edges in between things. How about there? Does this have what's now known as an Eulerian circuit? What are we looking for?
Yeah.
Yeah, there's an odd one, and there's an odd one. That was even, that's 2. We got 2 odd ones.
so if we start where one could be.
So while we can't have a circuit, because in a circuit really, nothing is the start or end. You can always imagine keep going around. But we could have what's known as an Eulerian trail or an Eulerian path here. Let me see if I can let's start at this one and make our way around. Go around the outside perhaps. Where do I got to end, by the way?
The bottom left one.
I got to end there. I think I just did it. So if you have 2 and only 2 odd vertices, you can form a trail like that. Otherwise, you need everything to be even, and then you can form a circle. It's fun. Here's another graph that I usually like to give in this as an example of this stuff, making kind of a triangular network. What sort of degrees do we see here? The corners are degree 2, so they're even, that's good. And these sides? You see how they're degree 4? So everybody's even. That means it ought to be possible to kind of trace your way around this graph without, lifting your finger and without crossing the edge twice and come back to where you started. Yeah, it's possible. Can you do it? What I would do is kind of go around the outside. Well, don't finish that off. Then go around here. Yeah, there we go. We start there, around the outside. Don't go all the way back to where you started because you need to end there. So, wow, graph theory got invented by Euler. That's not a small accomplishment. This is used for so many things that it's really mind-boggling. Today, networks, that's graph theory. When Facebook figures out who your friends are and targets ads at you based on the things you want, that's graph theory. They're using graphs to model your social connections. They use graphs to look at the connectivity of computers on the internet. So that's one more thing that Euler did. I got to try to fit the last two things in here quick. One of my favorite things from Euler's oeuvre is his formula involving e to an imaginary number. Have you guys run into e to the iPod?
+1 equals 0.
Yeah, that's a good way to do it. So why would you ever think to put e, the exponential function, together with complex numbers? Euler liked to deal with what are now called series, but in his time they called them infinite polynomials. So do you know what e to the x looks like if you put it into an infinite polynomial?
1 over factorial, 2 over 2 factorial. Well, yeah, x over x.
Okay, so I wrote the first couple of terms just writing them out, but Devontae, you were saying the right thing. What's the general term going to be?
X to the n over n factorial.
Exactly. So the shape of the terms of this is pretty simple. It just keeps rolling out. The dividing by n factorial is nice because you're going to get giant numbers in the bottom of these fractions as you go farther out, right? So each term is getting much smaller than the previous one. And x to the n grows, but not as fast as the factorials grow. So this converges. That's not an issue that Euler would have been concerned about. But now, once calculus got on firmer footing, we realized we had to deal with whether the series made sense for various x values. If you've done the stuff in series in Comp 2, the radius of convergence of this is infinite. So it converges for all x values. So what if you stick I times x in where x is? That's the weird little moment that Euler had when he realized that it would be fun. So substitute ix for x. So then you'll have e to the ix. Oh, wait a second. Do you guys know powers of I?
Yeah.
What's I squared?
Negative I. 1.
So I is, I to the 0 is 1.
Yeah.
I to the 1 is I itself. I squared is minus 1, because that's what I is about. This is the imaginary unit. What's I cubed? That's a hard one. Oh yeah, it's just negative 1 times another I, right? So you get negative I. And then I to the 4th? Oh! So wait, they go in a circle. So if you're in abstract algebra, you're seeing an example of a group of order 4. A cyclic group of order 4 here. The generator is I. You keep multiplying by I and it keeps going around in a normal cycle. So that'll let us figure out what this e to the ix is. It's 1 plus ix. But when it's ix squared, it's really minus x squared. And then ix cubed is going to be minus ix cubed. And x to the fourth over 24. What's that one? The fourth power of I is back to 1, so it's positive. So we just get x to the fourth over 24. That's cool. Now, you probably wrote more terms than this stuff, but I'm going to stop it here. Do you notice which terms have the I in them? Every other one, right? You have ix and ix cubed over 6. And Euler just recognized those as being the infinite polynomial for the sine of x. So the ones I just put the circle around, what would be the next one? Let's get the next one that has an I in it. It would be plus I times x to the fifth over 101. So that's another one. That's I times the series for sine of x. What do you think, given that this one is sine of x, the ones that are circled, what are the other ones that aren't circled in the infinite polynomial form?
Cosine.
Cosine, and they are. So 1 minus x squared over 2 plus x to the fourth over 24 minus the next one, that's an alternating series for cosine of x. This is cosine of x plus I times sine of x. He threw a pi in there too. Okay, pi. Just stick pi in, correct. So e to the I pi is evaluated pi. We get cosine of pi plus I times the sine of pi. Cosine of pi, that's negative 1. This one is 0.
0.
So e to the I pi equals negative 1. That's actually not the one Devante said, which a lot of people like better. If you add 1 to both sides of this, you'll get something that involves the 5 most important constants in mathematics. So you have one formula from 0 and 1 and I and pi and e. It's crazy. So occasionally you'll see math club t-shirts that say we're numbering negative e to the I pi. That's, you know, the joke now. Number 1. All right. So do I have enough time to talk about one last amazing thing about this? This is much more than that formula. That's known as Euler's formula, but it's really about his understanding that you could put complex numbers into series. And this is just one little tiny piece of the results that we got from complexifying the series mathematics. You can make a case for saying that Euler started topology, because one of the things he figured out actually is something that topologists use. Does anybody got to take topology? Is that part of your major?
I have to, because I'm not taking analysis.
Okay, so that's one of the alternatives. You can take topology rather than analysis. I'm a fan of topology. I think it's really a fun area of math. So, first, naturally, the way we do it is sort of the more serious, hardcore way. But there's an approach to topology that's really fun, and it's very visual. And so maybe you can, depending on your luck with who's the instructor, you can get some of that. So, Dr. Clark was some of the statisticians. The statistician, yes, he's not really. I tease him about being a statistician. This is not. It's not funny. I don't know why. So, topology has often been called rubber sheet geometry. It's like geometry if you let the surface that you're drawing things on be flexible. If you can imagine what happens when you have things that are drawn on a plane, but then you can distort the plane. You can move things around, you can squish it in or pull it out. That's what topology is about. So, like in topology, you can't tell a triangle from a circle. You start with a triangle, you pull on it in 3 different ways until it looks round, and you've got a circle. Right? And so the topologist can't tell the difference between his coffee cup and a donut.
So I wasn't bad at geometry, I was just a topologist the entire time.
That's right. So topology is interested in the shapes of things that don't change, the features of things that don't change when we continuously deform them. Okay? So things like writing the letter E like that versus writing the letter E like that. See, the topologist looks at this guy and says, that's the same as a stick. I can just unwind that thing. I can continuously deform it because I didn't close it up. Right? But I can't do that with this. I can turn that into a circle with a line dangling off of it, but I can't make it turn into a stick.
I can turn that into a theta. Turn into a theta.
I can't turn it into a theta either. That would mean sort of the opposite of breakage. If I had to reconnect things that weren't connected in the first place.
I mean, just hold on it and just push it in.
No, you can't do that. So continuous deformations will never take things that are separate and put them completely together, nor will it take things that are together and take them completely apart.
But it can't be overlaps, so that if it was in a 2D plane, it would look like the theta symbol, but in a 3D plane, it wouldn't actually be touching because it.
Let's see if we can. Well, it's such a good friend. I want to show you an animation that I know is out here. That was exciting. Watch it turn back into a coffee cup. All those changes that you just saw were continuous moves. If it was made out of Play-Doh, you could do that. Right? In fact, you could make a claymation video of a donut turning into a coffee cup.
Also,
Here's somebody's literally made out of
A
porcelain,
sequence.
a sequence of things where a donut and a coffee cup turn into slowly get deformed from one to the other. So this is actually one of your standard math jokes, that a topologist cannot tell the difference between a coffee cup and a donut. Because a topologist looks at that shit and goes, well, no, they're the same, they got one hole. One will hold coffee and the other won't, but still. Where's the hole in the coffee cup? It's not that junk, it's this. It's where your finger goes.
Did you also call them like philosophers because
Philosophers?
yeah,
Well, it definitely is a different way to think about stuff. I'm appreciative of this science. There's a whole lot of great stuff in topology. Let me tell you what Euler contributed to topology. He gave him an invariant that's called the Euler characteristic. So it's a weird thing because it's a number that you can calculate that's true of any graph that you draw on a surface. So think about I'm on a ball. So no holes. I'm not on a donut. I'm on a sphere. Right? And I draw a picture of a graph on that surface. Like maybe 4 dots and they're connected like so. Then I've got a certain number of vertices. In this case, it's 4. I've got a certain number of edges. What is it in this case? 1, 2, 3, 4, 5 of them. And I've also got a certain number of regions. There are 2-dimensional regions that this picture divides the sphere up into. There's the outside of everything, and then the 2 that you can see here. So the regions is 3. And these are going in a certain order. Vertices are points. Those are 0-dimensional things. Edges are lines that go between points. They're 1-dimensional things. And regions are 2-dimensional things. So what Euler realized, we can say this more generally if we call them V, E, and F, R, is that if you take the vertices and subtract the edges, but then add back in the regions, 2, you get 2. Always. That works for a sphere, and it also works for a plane. If this picture was in the plane, it would still be 1, 2, 3 regions. And what's this? But it doesn't work on a donut.
Because the extra hole.
You don't get 2, you get 0. You get 0 on the donut.
That's a negatively curved, right? No, never mind.
So I think it's, we can take a second to work this up for a donut. But I'm going to draw a donut in a way that you're not used to. It's called a torus, yeah, but it's still a donut. It's the outside, really, of the donut. But I'm going to draw it like it's a square. Yeah, that's a donut. You just don't realize it. What I'm going to do is have this top edge of the donut and this bottom edge of the donut really be the same place. Yeah. So if you ever play this game Asteroids, where you drive a little spaceship around and try to shoot asteroids? Well, if you go off the edge, you come back in on the other side, right?
Unroll.
Yeah. See, if those were really connected, we'd have a tube. This is distracting. I'm seeing this lady about rubber sheet geometry in the corner of my nose. I don't think you should take, your math stuff from somebody with that much hair.
So wait, you making fun of Brent?
He razzes me about baldness all the time. So wait, if I connect the top to the bottom, I've got a tube. Well, if I connect the ends of this tube, what do I got? You can take a tube. This is rubbery now. You can bend it around and connect them together. What you doing? Looks like an inner tube, right? So we also want to. So the way topologists will draw this, it's called a identification space. We're identifying the top and the bottom, but we're also identifying the sides. We all use a different symbol, a pair of things. But the identification doesn't do anything weird to you. You go off the end, you come back in, you're not flipping around. There is another thing that you can create where you go off the edge and you come back in, with the opposite tangent, you get reflected as you cross the boundary.
It's like Pac-Man, never mind.
No, Pac-Man doesn't do it. Like, if you look like the letter R as you left, when you came back on, you'd look like the Toys R Us version of the letter R. It reflect. You get turned inside out across the boundary. We're not going to do that orientation reversing business. We're just going to attach the top to the bottom, right? So let me draw you a graph in here. So let's draw the same graph, except we'll do our connections a little differently. I'm going to connect the thing that did go across the middle. I'm going to connect it by going around the tube. Goes around now. Right, so tell me, how many regions do you see? We still have 4 vertices. We have 5
6.
edges is 5. How many regions?
Oh, yeah, it's 5. It's 5. 2.
2.
3.
There's this one and this one. Oh, then there's this one. Oh, no, there isn't. Right? Because we can go around there and come back into this. There's just a particles 2. Or particles 2.
So 4 minus 5 is 2.
Is that 1?
It's 1.
Yeah, I was thinking this was 0. No, wrong. So anyway,
not 2.
the point is that you can come up with different numbers for different surfaces that are this quantity that Euler would calculate. Now, Euler didn't do it this way. He thought about it in a ball is happening on a ball. And what he was really interested in was the Platonic solids. Things like the tetrahedron, the octahedron, and so on. So try this with the. Well, let's see if we can make it quick. We got not much time. Let's talk about vertices, edges, and faces now, because if I have the tetrahedron, there's 4 vertices. You know how many faces it has? 4 also. How many edges are on that little triangular pyramid?
6.
Yes. And so 4 minus 6 plus 4. That's 8 minus 6 is 2. If you try this with, say, the octahedron, it's called the octahedron because it's got 8 faces. How many edges does it have? How many vertices does it have? I like to think of the octahedron as a pyramid, a square-sided pyramid with another pyramid glued to it. So you get 4 from the square bases and a top and a bottom point, and 6 vertices. There's 4 edges around the base of the pyramids, and then 4 more from each of them. That's 12 the first one. Is this working out? 14 minus 12? If you try the icosahedron, it's got 12 vertices, it's got 20 faces, and it's got 30 edges. What's your 20-sided dice? You know what your 12-sided dice is for? You know what that can be? That has, the numbers get interchanged in there, so that has 20 vertices and 12 faces, it still has 30 edges. Again, minus 8 plus F adjusted. All right, so sorry for going long. Next time, we're doing